Let me briefly introduce Daniel. Daniel used to, well, I think I want to mention he worked at NVIDIA for over a year, where he was basically optimizing some of the classical ML algorithms. So Daniel, correct me if I'm wrong here, but I think you kind of sped up TSNE, which is the dimensionality reduction algorithm, like 1000x or something, and then stuff like logistic regression, some of those very simple ML algorithms. But he was like, even back then, he was working on optimization, even though it was not deep learning per se. I doubt you worked with transformers back then at all. But you kind of got that optimization mindset. You probably got familiar with CUDA. You can tell us a bit more about that. And then when I noticed him was obviously on Twitter, when I saw you were just like solving bugs like crazy and contributing, and people started noticing that I follow as well. And so that kind of, when I see multiple sources kind of like pointing into the same direction, that spikes my attention. And I saw your work. I was really, really surprised. Like, and I told you this offline as well. Like there is so many senior folks and brilliant folks I met over my career, but like you are definitely one of the like stars I've met personally so far. Like technically speaking, the stuff you've done with Trident and writing gradients and the speed ups you got and VRAM improvements you got, it's just mind blowing. And so this presentation, this talk today and chat is going to be Daniel walking us through his basically debugging process and how he thinks about solving problems, and we can kind of go through the set of bugs here for Gemma, and we can kind of go one by one and see how he thinks about solving problems, if that makes sense. So with that, Daniel, welcome. Hey guys, I want to give a huge shout out to Hyperstack folks who have generously sponsored my compute over the past month or so. Basically, I got 16 H100s, which is 2 8 GPU nodes, and the performance has been amazing, basically 2x the speed up compared to my A100 nodes. So I want to quickly show you how you can get started yourself. It takes basically 3 steps only. You go to the environments here, you create a new environment, you give it a name, you pick between Canada and Norway. That's the first step. The second step, you go to SSH keys here, you create a new pair, you pick environment you just created, you give it a name, you paste your public SSH key. That's it. And finally, go to virtual machines, deploy new machine, give it a name again, select environment. Let's select Canada here because they have more compute there. Then you select the hardware you want, like for example H100s. You select the images, you select the SSH key you just created, and hit deploy. That's it. Literally a couple of minutes to get started. It was really easy for me to just basically create these 2 nodes I just mentioned and get started running LLM trainings. So the documentation is super cool. I could actually solve all of my problems just by looking at their docs. They additionally have a Slack channel where they were super helpful, so I can't recommend them enough, honestly. The thing they kind of focus on is basically, because a lot of these GPU providers focus on big enterprises, so oftentimes you can't get on-demand H100s, whereas NextGen focuses particularly on that. You can get top-of-the-line hardware on demand, even if you're individual or like a smaller team or whatnot. They also focus on bigger companies, but that's kind of their edge here. So without further ado, guys, let's go back to the talk. I do suggest you check them out, and let's continue.
Yeah, well, thanks for introducing and like inviting me. Much appreciated. Yes. So yeah, I used to work at NVIDIA, like making TSNE 2000 times faster and other like randomized SVD and other algorithms faster. And yeah, so like I've never actually touched transformers before, like during my NVIDIA time. I think I didn't really like transformers before. I would just focus on classical machine learning, and yeah, but like the experience of the math calculations and like all the math stuff brought over to like, you know, what we do in Unsloth. And okay, yeah, but I will start off. So like, if people don't know, like, so Google released an open source model called Gemma a few months ago.
Sorry for interrupting. Yeah. Maybe before we go into bugs, can you briefly tell people who are like, how old are you, if you can share? Like,
oh, I'm 26. Yeah.
You're 26. Okay, so can you maybe briefly explain like how does one, like with your age, like how did you pick up so many techniques and like how did you get the courage to start writing gradients like manually? Like many people know this theoretically, you know, but like they don't have the courage to just question the autograd of PyTorch or whatever framework they use. So like, can you maybe just like shed some light on your mindset and how did you pick up all of the knowledge there? And then we can get into the bugs.
Yeah. So I think like, so I do kind of have a maths background from uni. So I did a major in like data science, computer science and maths. So like kind of my maths isn't actually very good. I kind of like nearly failed a few courses, so it's actually not very good. But I think the problem is like, uni maths and like, high school maths is like, they just do rote learning. And I always like to ask questions like, how do they even like come up with this formula? So like, I think that's probably where it comes from. And like for differentiation, for like backpropagation, yes, most people just rely on like backprop and just, autograd and don't really care about like exactly how to derive the derivatives. And I think like, I'd like to like formulate on like pieces of paper, like, there's like tons of notes on my side. There's like notes. And like, I just write down all of the derivatives by hand. And like, for example, like you start off with like the logistic regression, which is essentially like a 1-layer neural network. How do you derive the derivatives? How do you do backpropagation? And then you scale up to like 2-layer neural network, 3 layers. They're all the same. Like once you like know how to do 2-layer neural networks, you could do like, thousands of layers. They're all the same formulas. And it's like, it's just a recurrent formula. And so like just doing the differentials is very hard. And it took a lot of time to like, visualize it in my head. Like, how do we actually do the differentials? How does the matrix, like, how does like the matrix, like A times B, how does like the formula work? And like, how does it actually stack up in my head? And like, okay, there's like some random stuff that happens in my head. And then, yes, I can like kind of visualize the differentials kind of. And then that's kind of like how the differentials come out. But that's only for the backpropagation. The bugs are just like reading through everything and like, oh, there's a bug here. It's like just like random chance. Yeah.
Perfect. And I saw that for some more complex like backprops, you did use some software tools to help you. Like, why was that? Was that because some of that was just very hard to derive, and then you kind of copied that part and put it in, and then you kind of combine it with your knowledge, or what's your like general process when you work with tools as opposed to just with paper and your own mind?
Yeah, actually, I can share Desmos. Okay, I can't really spell Desmos, but Desmos, right, is one of my favorite tools, right? And like, for example, if you want to do the, y is equal to, just the like, one, right, very famous, right? Sigmoid, right? Simply, you can just do the derivative, right? Like, I don't know if people even know that you can do the derivative in Desmos. You can also do like integration, right? So like integral, I think it's integral, right? Negative infinity to infinity, right? And then like essentially you derive your derivative over here and then you minus it, and then like some derivative fx minus, right? And then you do the dx, and then you get like some sort of number. And then yes, we use like so I use Desmos as like a verifier. Something you can't rely on like differentiation yourself. You never know if you get something wrong. You don't know that. And so like you have to use Desmos to like approximately guess what's a derivative, and then like just verify. Yeah. Got
it. So it's more of your verification tool as opposed to something that derives the whole equation for you personally. So you just do it as a post-processing step, so to speak.
Yeah. So like Desmos does not actually allow you to like derive the actual, like for example, okay, it can tell you the blue line is a derivative, right? But like, what is the formula for this? It doesn't tell you that. And so like it does this by numerical methods. So you still need to derive it yourself.
Got it. But like, so sorry for interrupting. So do you then plot your own gradients and compare the curves, or do you use something like Mathematica? I think there are those symbolic engines that actually give you the derivation and the actual gradients in a symbolic form. Did you use those as well?
Yeah, so like I did, so I do use like Wolfram Alpha sometimes for like some of the derivatives. It's not very effective because it can't actually do, it can't like derive it correctly. Like it's actually not very optimal. So like you do have to change the formulas. I'll probably share later, like, how do we do like, but like derivatives, for example, like the tan H, the tan was very complicated, and Wolfram Alpha provided some solution, but it was so large, like, the derivative that was horrifying to like, manipulate.
Yeah. That makes sense, because for 10H and sigmoid in particular, there are very nice expressions where you can reuse the output and not have to even have the input, right? For 10H, was it like 1 minus 10H squared or something? I forgot on top of my head. But like, I assume that Wolfram would give you the actual equation without doing that reduction. That's more of that's something that a human has to have, like ingenuity and kind of refine the equation and have it in a very compact form. So I think that's what you're referring to when you say it's kind of not usable in that form. Makes sense.
Yes, exactly. Okay. So you need to, that's correct.
Having said that, I think let's jump into bugs, and then we can kind of go back to this. I think this was helpful just to see. Maybe a quick question is: do you actually draw your curves when you're comparing with Desmos, or how do you compare with it?
Oh yeah, so you mean like manually draw the curves, or do you mean like?
I mean, using Python, whatever. But because you said you're using it as a kind of sanity checker.
No, I don't. So I don't actually use Python to like manually do the derivatives for like drawing it out and then like check. I just use Desmos directly because like all of the working is on paper. And then like I just like put it into Desmos and like check. But that's only like one part of the whole process. Like for the activation functions, that's generally I just use Desmos. But the rest is like manual checking and like I don't think so. Bug fixing unfortunately cannot be automated. It's actually very complicated. And because like a bug can like come out from here. And it's unexpected, and then it comes out from here, and there's like many places there's like bugs, and each of them can like interact weirdly with each other, and so like it's actually very hard to automate away. And I guess that's the only human part that is hard. It's like essentially finding bugs, like the AI itself. Like it's actually kind of funny. I'm assuming there won't be bugs in AGI. I'm assuming the AGI will find bugs itself and fix it itself. But like who knows? Yeah.
Yeah, that's the idea. That's the premise. Okay, let's maybe start with the Gemma bugs. How do you want to approach this? How can we start?
Yeah, so like I shared a post a few months ago about like Gemma bugs. We also found bugs like, for example, Llama, Mistral, V3. But I think Gemma is probably where Unsloth is most known for, and the work that I've done is from Gemma. And the first one essentially is like, you have to add a BOS token, so the beginning of sentence token. Actually, I think when it first released, it actually did not add a BOS token, which is very interesting. And how do we actually find that was, if you look in the paper, you have to read the paper, the Gemma paper. It kind of like says that you do, I don't remember where, but you do need to add a BOS token. And to verify it, we actually did verification. So if you look at the loss curves, if you don't add the BOS token, right, the loss curve is the blue line. Oh, did it?
Oops,
did it go
I
away?
think, yeah, I think you stopped sharing accidentally or something. Seeing Daniel debugging in real time. Perfect. We see that.
Apologies. Yeah, my own problems. Yeah, okay, technical. But like so essentially what this shows is that, if you use no BOS token, the loss curve was the blue line. So you essentially have to run a fine-tuning run. So every single time when you want to find a bug, you need to run a fine-tuning process to find these issues. And if you don't add the BOS token, the fine-tuning loss is the blue line. And then if you add the BOS token, it's the red line. So clearly you have to add a BOS token, right? So like if you just look at the loss, the red line is definitely correct. And the yellow line is a new methodology called packing, which like language models use to speed up the training process. And what they do is they take small sequences and then they shove it together and then they train this. This can actually speed up training a lot. Now the problem is that Llama and Mistral, if you do this methodology, pack sequences together, your loss will still look like the red line. But for Gemma specifically, I didn't actually understand why the loss curve for Gemma, if you do packing, the loss curve was the yellow line, which was actually very weird. And the fundamental reason, I was trying to ask the Gemma team about this, and if you look in their the T4 paper,
just a quick question about the loss. If you can go back there. So I agree that the red loss obviously starts being the lowest, but then it looks like the yellow one converges to a lower loss. So then how do you kind of make a trade-off there? How do you think about what was the right process? Or
Oh, the yellow loss, yeah, convergence. That's probably incorrect. Like because like once it goes to a high loss, and then you have like a learning rate, which I said, once it actually goes down the hill, and then like it's just by coincidence that it's actually lower loss. I think the graph that I did is incorrect. So this is actually not good. And also because when you pack sequences together, you can actually have lower loss because the sequences, when they see it together, it's actually like it's as if you're cheating in the like model, and so like it's probably not a good idea to this. So this yellow loss is actually incorrect. Yeah, you should never see this yellow loss. Yeah.
What was the reasoning? How do you know it's incorrect? That yellow loss, like just because it starts being like higher in the beginning, or?
So generally speaking, like when you do a fine tune of a language model, the loss should start from around 1 or 2. It should never go to like 10 or 5. That's actually very incorrect. And so like when you go to 15, it definitely is incorrect. And because remember the loss is just a cross entropy loss, and it just shows the probability, like it does the average of all the probabilities of the next token. And if the loss is like at 5 or 10, that means the model's not really, it's useless essentially, right? The loss must be 1 or 2. That shows that the model's actually learning. And that's why like this loss is definitely wrong. So whenever you do a fine tuning, whenever you start fine tuning and you find your loss starts at 10 or 5, right? Something definitely is wrong. And so, yeah, that's just by experience.
That makes perfect sense. That's basically if you compute, if you had a random model initially and you do minus log over the 1 over the whatever is the size of the vocab, you'll get what a random model baseline is, and then you can kind of go from there. Okay, that makes sense.
Yeah.
And then you can kind of see that the yellow one was quickly learning how to adapt to that new out of distributions training strategy and then converge to even lower value, which is crazy. But okay, sorry for interrupting a bit more here.
Yeah,
Thanks.
but just pretend you didn't see the lower loss. Just pretend. Just the first part is incorrect.
I actually just computed. I computed log over 1 over 50,000, which I think Gemma's vocab was something like that, and that's roughly 10. So when you say 10, 15, that's precisely what you were saying. That means the model is completely outputting random logics in the beginning, and that's how you kind of know that something is wrong there. That makes sense.
Exactly, right, exactly. So like if it's a 10 or 15, it's definitely incorrect. Like it's literally useless. It doesn't even know what the model, like it doesn't even know what's the next token. You'd rather not use the model. And so like if you see like a 10 or 15, that's definitely wrong. You must be around 1 or 2, you know, like 3 is okay. I think 3, 5, if you see 5, there's some problems. Yeah, like 1, 2, 3, somewhere around that. Yeah.
Mm-hmm.
So I think the second, so that's the BOS token problem. And the second one was actually a paper typo in the paper. Yeah, so there's actually a paper typo. If you look in the Gemma paper, there's actually a typo for, I think they fixed it now. But if you look in the paper, right, if you see this part, right, they added model afterwards, and another one over here, right, so end of turn model. This is actually not correct. If you look in the paper, which they corrected, right, there's no model anymore, right? So they corrected.
You can go. You can modify the URL. There is v4. If you see the suffix, you can do v3 or v2. You'll see the old version of the paper, so you can actually see what it looked like initially. If you see, so in the URL, just replace the suffix v4 with v3. I think.
Oh, I think v1. No, I think v1 they also edited as well. So v1 is actually not. I think so it's actually they edit. I don't know why, but they also edited this one as well. So v1's also correct. So I think maybe, yeah. So v1 is also, I don't know if there's a v0, but I'm pretty certain when I screenshotted it, it was actually this. And so like that was they did fix it though, which is good.
Makes sense. Makes sense. And quickly going back to the BOS. So other than you running these 3 different runs with no BOS, with BOS and TRL packing, was that the only way you find out, hey, we just have to use BOS? Or did you do anything else? Did you actually go to the code and analyze stuff?
So I think generally speaking, like when you tokenize a sequence, you inspect. Okay, generally what we do is like you have to first inspect the training loss first, and then if it doesn't match, then you're like, okay, what's the next step? And then you look at like you look at the tokenizer, you look at the input IDs, you look at like the entire process, and sometimes you can see like, oh, okay, the input IDs are there's a missing BOS token. So like I guess once you inspect it, you can kind of see where these issues come from.
Makes sense. Thanks.
Okay, going on. So yes, there's a paper typo, and then one of the most interesting typos was not really one of the issues was so if you look in the Gemma code, now you have to actually look in the Gemma code. I think yes, okay, that's a Gemma bug fixes. I have actually code going on. If you look, for example, like in the attention, right, there's like this issue of when you do the rope embeddings as well, they downcast the attention, they downcast the rope embeddings to like compute D type, which is actually incorrect. And this is actually relevant to another bug that we found. This is for Llama and Mistral. So this is like a long story, but like in Llama and Mistral, there is another issue, which I will show. Give it a second. Yes, so these bugs are all correlated to each other. I think where did I put it? I have to scroll to find it.
But the bottom line is you don't want to downcast to 16-bit precision, bfloat 16. You want to keep that at a 32-bit precision, right? And that's something that you kind of empirically have to understand, because when you go to longer sequences, the fact that you don't have as many mantissa bits causes the actual value to be incorrect, and that's something I think you kind of showed on the blog. If I'm following you correctly.
Yeah, so when you do the rope embeddings, one very be careful you have to do is like when you downcast, when you don't use the autocast correctly, because like when you do training, when you do like fine tuning and training, you use bfloat 16. Most models use bfloat 16 because you get 2 times speed up. And the problem is if you accidentally use bfloat 16, you might be actually downcasting everything. But so CUDA has this weird thing where it downcasts everything if you don't set it explicitly. And so all of the rope embeddings got downcasted to bfloat 16. And if you do that, actually you will get very bad. So this is a previous error where I think I put it somewhere. Where did I put it? You'll get so this one. This, if you look over here, right? Keras, if you downcast to bfloat 16, the positions was 8192, 8192, 8192, which is totally incorrect. You actually overflowed as well, right? You're not. It's if you do sequence f of 8192, right? The last number should be 8191, right? So like, just be careful of like the indexing, right? And so Keras was actually totally incorrect on TPUs. When you use Gemma's official implementation on TPUs, right? The number is correct, right? So 818. 8189, 8190, and 8191. And essentially the problem is that the downcasting was not supposed to be there. You're not supposed to downcast it to bfloat 16. And if you downcast it to bfloat 16, you will get precision issues like these issues. And this actually can affect the training loss dramatically, especially for long context fine-tuning. When you do like long context training and long context fine-tuning, you will actually misrepresent the positions. And for shorter ones, it's fine, right? So like if you, for example, if you do like location 1, location like 2, location 3, they're okay. But once you go to like very long sequences, you will have errors.
What I'm thinking here is, why not, like, if you, instead of creating the ops range with float 32, if you were to just do it with long ints and then cast to bfloat 16, will you still have the same issues because bfloat 16 simply does not correspond nicely with the integers and then kind of messes things up? Do you think that could solve it as well? If you understand what I said.
If you cast it to long, it's so the problem is if you use bfloat 16, you must cast it to float 32, right? Because this is a it's not an integer, it's like a you have to be careful on that as well. But yes, you can cast it to long, then you cast it to float 32. But the problem is when you use torch autograd, when you use autocast, it will remove all of your casting anyways. So like you have to be very careful. And so like in order to solve this issue, you must disable autocasting, right? So this was I forgot GitHub does that. But like you have to so this is a thing that we found before the Gemma bug fixes. And this affected like Mistral, Llama, and other models. Which used, I think Mistral was actually fine actually, but I think just Llama. So Llama's fine-tuning was actually incorrect as well. And you have to downcast this area by turning it off. So like you can't actually downcast this area. You must turn it off.
Got it. So you can't, even if you explicitly say to whatever BF16, it's still going to override your literal explicit casting. That's what you're saying with
correct,
the
correct. Yeah, so PyTorch is so CUDA autocast is just very weird.
Bad.
Like so like even if you do like for example, look at over here, right? We upcast a float. That's still not going to work. Because the problem is when you do the matrix multiplication becomes bfloat 16. And so like you have to force that to be float multiplication.
Got it.
That was one of the issues.
You don't have a way to use PyTorch syntax and to say this matmul is going to be float as well, because usually you just let it infer from the operands. And here you're saying that basically the autocast messes it up because you cannot explicitly annotate and say, hey, I want a matmul to be also in float.
Yes, correct. So you can't actually explicitly tell it, we want it to be float, like a D type, which is float. And so like that's probably the reason why you have to be very careful. To like these specific areas, you need to like downcast correctly. If you don't downcast correctly, then your results will be incorrect.
Do you know if PyTorch team is working on fixing this? Because this doesn't seem like
it's not really I wouldn't say it's a bug. It's more like the implementation person's problem. Like it is. So PyTorch does say that you have to be very careful with using autocast. It's more like an engineer's nightmare. Like you have to carefully put this correctly. And if it's just rope embeddings. It's just rope embeddings which have this problem. Other embeddings don't have this issue. So it's just rope, which specifically has this annoying autocasting problem.
Yeah, I'm just thinking how this could be solved from the framework standpoint. In the sense, you can maybe instead of using get symbol for matmul, just call torch matmul, pass the operands, and specify the actual compute type of the operation, right? As opposed to having it being inferred from the operands. That would be
you could do that, but then
quite a more robust, and then you wouldn't have to do like this automatic disabling, which is kind of ugly.
So I think Jax like from Google probably does that for you automatically. Like, that's probably why Jax is very popular as well. Like, for the high performance people, like, you don't have to like manually find which area is autocast, which one's not autocast and stuff like that. But I think that's the whole point of PyTorch, is it makes it so easy for people to use. And so like, I think if you do add these components, it might overcomplicate the entire process. So like, I think like for this, specifically just for this, like it's already all in transformers, like, for Llama, for Mistral. If you look at everyone's implementation, like this, our fix kind of like solved all of their problems in one go. You just have to copy paste correctly. And so like, I think most people just copy paste this entire code. And if you look at everyone's implementation, all the fixes there already. So it should be fine for now. Yeah.
Thanks.
So for the next, so that's a previous bug that we fixed before. But like essentially there's like other issues. These are all auto casting issues. If you look in like, if you look in the code for Gemma, if you look at the code for PyTorch, and if you look in the code for Keras, they all have these weird auto casting issues, and downcasting, upcasting. If you use the bfloat 16, it has to be in some specific format. And if you don't do that correctly, then you'll get incorrect results. For example, one of them was like the square root of 3072. Right, the actual answer is 55.4256. But the problem is in the Gemma implementation, you have to actually downcast this to bfloat 16. And if you downcast this to bfloat 16, it's actually 55.5. Right, and so like these small little differences, you have to be very careful. And if you don't do this correctly, then your results will have some, negative result for the fine tuning. It won't be too much effect, right? So during the fine tuning process, or the training process, the model will learn to adjust to this new number, but you should still get the correct implementation to have lower loss. Yeah.
Got it. And to catch this one, did you actually have the reference loss curve, or how do you compare? How do you know what's the ground truth when catching these small numerical differences?
So you have to compare the three implementations. You look in the Keras implementation. For example, this is the Keras implementation. You look in the actual transformers implementation, and you look in the, I think this is the Google one. Yes, you look at the Google implementation. And if you look in all three implementations, you can kind of see, okay, this one's doing this thing, like it's downcasting. This one's doing another thing. And then the other one's doing something else. And then now you have to do like, okay, which one's the most correct? Now you have to like look.
If any of them, then you can think from the first principles and see whether any of them is actually correct, because you see variance, and that's already suggesting that they don't know what they're doing, or maybe one of them knows what they're doing.
Yeah, I would normally trust the Google DeepMind team, like the original implementation, to be correct, and then the derivative implementations are probably the problem. Like maybe the Hugging Face team has like this small problem, maybe this one has this problem, maybe this one has this problem. But in general, I essentially just ask all of them. I ask the Hugging Face team, I ask the Gemma team, I ask like all of them, which one's correct? And they're like, then they have to like, okay, maybe most likely this one's correct. And then, it's like a discussion that we have to have in general. Yeah.
Where do you communicate with them? Is it on your Discord? Do you ping them on Twitter? Maybe that type of information is also useful to folks listening.
Oh yeah, we know, we generally collaborate with them on Slack. We talk to them on Twitter. Like, they're very great people, and the engineers are very fantastic. So yeah, we just collaborate with all of them to like try to see which areas of which, like, is this a problem? Is this not a problem? They're generally very, very responsive, and so like, I give high marks to them. Yeah. So these problems are just very hard to find. I wouldn't really blame them for it. It's just very, very complicated to find. Yeah.
No, of course, that's perfect. And just want to look back to the thing you said about DeepMind being correct. The thing is that how you kind of qualitatively describe what being incorrect here means is deviating from the official implementation. But because you're trying to fine tune, and so if they had any bugs during training, you actually don't want to change that. It's almost like legacy code. You just want to stick to whatever was there, right? And so from that standpoint, it's not like you can correct, even if they had some bugs, you kind of have to assume that's going to be ground truth. You don't want to deviate from the training, otherwise you'll be out of distribution for the training, right?
Exactly. Yeah. So like, for example, like the packing issue, like, they should have probably trained it, with, fixing the packing problem, because like Llama Mistral doesn't have this issue as well. Like, so like technically they should have retrained the model, but it's not that serious. So like, I think in general, what we do is like, we follow whatever the official implementation is to get the correct results. Whatever they, did, we should follow them. Otherwise, yes, as you said, like, the result might not be correct using these other implementations. So we have to follow the original one.
Makes sense. Well, what I'm trying to say, even if you were correct, you might get suboptimal results, as opposed to being incorrect in the sense of being consistent with whatever was the reference implementation. That makes sense.
Yeah.
Thanks for clarifying.
And the other one is like llm, for example, like it has to be done in float 32, or the entire process. So I think in Llama and Mistral, what they do is they actually downcast to bfloat 16 before And so like there's some ordering of operations that you have to do, like, where do we actually upcast, where do we downcast? And this essentially all you need to do is look at the code. So I put like 3 different implementations. I think this one, so that's a Keras implementation. This is I don't remember what this one was, but the other one was the actual Gemma implementation. And essentially, if you look at the location, if you look at the location of the downcasting, it depends on where you actually put the downcasting, and it's actually very, very important. So if you look over here, like the original Keras implementation, you downcast, you go back to float 32 at the very, very, very end. But then the problem is in Llama and Mistral, which is what people copied, they actually moved it to the second point around over here. They will downcast. I think if I have I can probably find it. Yes, where's the RMS? I need to find it in the code. Where did it go?
Just control F it. I mean, but do you have any first principle thinking about casting in general, or do you just? I think I heard you talking with the PyTorch folks, and you said it's mostly empirical. You just try a bunch of stuff and see what works. But like, have you formed any actual mental model of what computation is sensitive to what type of bit precision, and anything of that sort you can share?
Unfortunately, it's a combinatorial process. I just have to try all of them. It's actually very hard to find which precision is the correct precision. The worst part is when you do deriving of the derivatives and you don't know which one to cast. That is a nightmare. That is actually, I can show you. Wait, let me show. I can show you like a problematic. I can show you some code which is like extremely annoying. I can like, for example, if you go to Unsloth GitHub repo and like if you go to like, for example, Swiglu, our Swiglu kernel, right? If you look carefully, okay, let's go to the derivatives, right? Look over here. I specifically, there's like 3 different derivatives that you have to get. Like, you load in the matrices, you load in like, each vector separately. Like, why did I comment out this for float 32? Why is it only this one float 32? And why is this one not? And this all depends on trial and error to see which one is the correct one. And you have to like try all of them to see which one has a loss, which matches exactly. So normally speaking, you would trust the AutoGrad engine to be correct. So you just trust AutoGrad to be correct. And the goal is, how do we like manipulate the the downcasting and upcasting to equalize to the actual PyTorch implementation for AutoGrad? And if you just do upcasting for the the E, if you do E row, whatever, this variable, that's fine. But if you upcast the other ones, you will get incorrect results. And unfortunately, this was all like manual. Yeah.
The only issue with that is obviously you're now trying to do something very pragmatic. You're trying to enable folks running on like Colab or whatnot in a very easy way to fine tune and get something very pragmatic. But the problem with this approach is if somebody later tries much larger context length, numerics change all of a sudden, and something you hard coded which was empirical is maybe not going to extrapolate to that setting. Or if you change a device, I don't know, if you go from one device to another device, maybe that trident gets compiled to a different PTX sats or whatnot, and then you end up with different numerics again for that device, and you source some other problem. So that's what I'm trying to see. I see this casting issue has been plaguing you a lot and the community as a whole. And I'm just thinking if there is some smarter way we can approach this other than just trying it out on a limited number of use cases. And if that works, you kind of assume it works elsewhere, but it doesn't have to, right? That's the issue I'm having as a purist, as an idealist.
There is one way we can solve all of these issues, and just simply use float 32. Like, don't use mixed precision like B float 16 or float 8 or float 4. But I think the problem is we want faster training. We want if you go to like float 8, we want 4 times much faster training. And so like that's probably the reason why we have all these issues. So essentially, our life could have been much easier if everything was float 32, and we don't need to worry about anything.
Of course, we can go to 64. We can go to double precision as well. But then you kind of NVIDIA optimizes the smaller the precision, the much faster, like exponentially faster the operation. So of course we want that speed, but we still want the correctness. So how do you find that trade-off of, hey, this is fast, but we know it's going to work?
So we are actually working on something which is like automate some of the processes. Like, can we like, automatically find all these issues, do auto casting and stuff like that. But I think in general, generally speaking, if we like if we like know that the transformer architecture is generally completed, we don't have to like do all this methodology like every single day. So that should be fine. But like once a new methodology comes, we generally rely on like, is the autograd engine correct? If the autograd engine is correct, then we say like, okay, assume which part do we autocast? Do we like autocast this one? Do we like change downcast this one? Do we downcast this one? It's just that. It's not gonna like take too much time because like, if there's only 3 to do, right? It's not that many combinations. And so like it's okay. Right. So yeah, I think it's 3 factorial. So I think it is. Yeah, it's 3 factorial. So like,
but you still have to choose the computation, right? You still have to change. You still have to choose. You have a decision of what computation happens, even though your operands are in whatever type, right? So I think the combinatorics explodes very quickly. But anyhow, I don't want to spend too much time on this. I understand it's very empirical right now. I'm just complaining that we might be able to do better.
Yeah. Hopefully we can. Yeah. Hopefully we can fix all these issues. Wait. Let me just. Okay. The next. Okay. That's the road one that we discussed about. And also the like very interesting thing is that if you actually do all of the changes, if you use different positions, we actually showed the L2, the log L2 norm. And so if you show, the original one was a red curve, right, which is very high error, which is actually not correct. And if you add all these like changes that we did, you can essentially move the error down. And we showed that if you add all of the changes up together, we can get the black curve, which is the lowest error, right? So like, remember this is log scale, right? And so like penny minus 1 is like 0.1 error, right? 0.01, 0.1 error. And originally the error was 10, right? So like that's definitely incorrect. So we reduced the magnitude of the error by dramatic amounts. This is log scale. So like it probably doesn't look that dramatic, but because it's log scale, we don't want to like show the errors like that big, right? If it's like over here, the error is like, 100 or something, right? Which is definitely not incorrect. Definitely not correct.
Can you just clarify what's the norm of? What do you do? Like, do a difference of gradient tensors between the reference and your implementation, and then you find the norm of that vector, or what's the actual norm we're looking at on the y-axis?
Yeah, so we generally assume the DeepMind implementation is generally correct. We obviously like had to edit some issues in the DeepMind implementation, like the paper issues, which BOS token, and like other stuff like that. But if you assume the DeepMind implementation, the reference is correct, we just compare the rest with the DeepMind implementation, and you compare the L2 norm, like, how far is this from the DeepMind implementation? And you can kind of see, okay, if we change this part, can we get closer to the actual reference implementation? So we just assume the DeepMind implementation is correct.
Makes sense. And you're talking about activations here or gradients, or that's what I'm trying to understand. What's the quantity on the y-axis that you're looking at?
Oh yeah, so the final layer output. So this is so the x-axis is layer number, right? So like the output of the layer, we find like, what is the difference between the DeepMind one and the, PyTorch or, PyTorch Keras one or the Hugging Face one, and what's the difference? And we just do the L2 layer, L2 log, the log L2 norm for that. Yeah.
Cool. Awesome. Now it makes sense.
And obviously, so the rope one, which we showed, like, the fix which we showed in Llama, Mistral, all of them, right? So we showed that if you fix that, you can reduce the loss, like literally you can reduce the loss, to the red curve. And originally it was a blue curve. And you can see at every single step, the loss is always lower. And so like, that was a very important fix. That's in Gemma, Mistral, Llama, like, all of the models that you currently, like most people use with rope. And obviously the most famous one that we did was the approximate GELU one. So in the PyTorch, in the Keras implementation, they use approximate GELU. And in Gemma's PyTorch, so this is the actual, official implementation in the PyTorch for Gemma, they used exact GELU. And in Hugging Face, they also use exact GELU. And the correct one is you must use approximate GELU. So yeah. And so you can't actually use exact GELU. And
so in this case, you're saying that the reference implementation was also incorrect. Is that what you're saying?
So the reference implementation used the approximate GELU, but we don't actually know, like, depending on which one is correct, like, you have to follow the reference implementation, as you said, like, if you don't follow the reference implementation, then you get wrong results. So the reference implementation used approximate GELU, and so everyone must use approximate GELU, right? You can't use, like, exact here, exact there. And so, like, there were two, so the Hugging Face one and the actual Gemma itself, like, one of the other packages, used exact GELU, which was actually incorrect. The Keras one was correct. They used approximate GELU. So like, sometimes the Keras one's right, sometimes the Gemma's one's right, like everyone is like right in their own way, but they're technically all wrong. And so like each part was like, this part was wrong, this part was wrong. And so like, it's like mix and match essentially. Yeah.
Just a quick question. Why don't you have a reference implementation among these 3 snippets here?
Okay. For the Twitter post, I can't actually paste it in, but in the reference implementation, you can probably see, I think it's in the DeepMind one. You have to actually find it. I have to go through the, I'm pretty certain it's I think it's in modules probably.
It's fine if you can find it. It's fine.
Yeah, it's somewhere. It's probably somewhere in. Yeah, it's definitely somewhere in here that they call feed forward. I'll see GELU, right? So like they call GELU, and this is Flex GELU. So you actually have to type Flex GELU
and see what's the default setting for the approximate. Okay.
Yes, exactly. So
and it's like it's false.
Yeah, right. See, approximate is equal to true, right? So they use approximate GELU in the official the official implementation.
Yeah. And so somebody, when they were copying over, they just saw, okay, this is an GELU, let's call it GELU, assume the default settings are the same, which turns out not to be the case. That's how bug probably came to be.
Exactly. So like if you go to the PyTorch implementation, I think GELU is not. Oh wait, they go to the function.
It's likely
it's none.
Yeah, exactly.
Right?
Exactly.
So like,
it's quite.
So you have to.
Framework fun. Assuming defaults are the same is not a good idea.
Yeah, exactly. So I think that's the majority of the Gemma issues. Obviously, we found like other issues, like in V3. If you look at, like, for example, if you go to the V3 config.
Sorry. Before going there, because otherwise I think we'll expand too much and people will lose. Let's maybe focus only on Gemma. And if you can go back to number 7. I didn't quite get what that one was about. I saw the curves are different, but so that one rope should be float 32. So it's again some casting issue.
Oh, that's the one with the stuff over here, like this one.
So that's the same thing.
Yeah. So Gemma specifically had this issue, but they had other issues. I just put the picture together in the post. But like this was the main issue that they had, was the rope casting. If you cast it to be float 16, then it's incorrect, right? So like the positional encodings are not supposed to be downcast to be float 16. It must be float 32.
Mm-hmm.
It's just a rope. I guess it's just a rope issue. Like rotary embeddings just have this issue. You must, use float 32. Otherwise it won't work. Yeah.
Makes sense. And so if we could zoom out and take a look at your problem-solving approach here holistically, how I understand it is basically a model comes out and you do 2 things. On one hand side, you're actually running and observing the curves. On the other hand side, you take some of the most famous frameworks, be it like PyTorch, JAX implementation, Hugging Face implementation. You cross-compare them and see whether there's some consistency, and if there is an inconsistency, that's a good hint that you should double down on that bit and see what's going wrong and who is wrong. So at least one of them has bug, and you can submit if nothing else, a pull request to that particular repo if you have time, obviously. But is that roughly how you're kind of thinking about this on a high level when a new model comes out?
So I think when a new model comes out, like for example, like V3, for example, if you look at V3, they just come out with some sort of new model. We essentially inspect their config first. We look at like the entire model, like, is this a correct implementation? Like, what is this implementation even like, relevant to? Like, and we notice like, okay, so V3 is using the same architecture as Llama. It's the same architecture as Mistral. And so we inspect it, like, okay, can we see in the config file, is it actually a Llama model? But then if you look over here, there's like a sliding window, right? And so it's like 2047, right? And you might be wondering, why is it 2047? Shouldn't it be like 2048, right? And so like this is actually a bug. I don't know why they still haven't fixed it yet, but like actually they fixed it and then they unfixed it. So I probably need to, I need to tell them again about the problem. Yeah.
As soon as you get familiar with low-level GPU stuff, and I've been dabbling in llm.c over the past weeks, like as soon as you see something that's not divisible, but by at least 2 or 4 or even 256, like that's a big red flag, like because it's going to be very slow when you boil it down to actually kicking off kernels on the GPU. Stuff run much slower when you don't have like nice numbers. So that's a good hint.
Yeah, exactly. So like you also look at, for example, like the pad token is 32,000, right? This is V3, and the EOS token is 32,000, and you have to be careful. You cannot set the pad token to be the same as the EOS token, for example, right? So like if you do that, then if you do masking out, then the EOS token, the loss will be ignored. And so like the fee model will like, if you fine tune a fee model using this incorrect config, then the model will just like spit out garbage forever, right? It will never stop It would never stop, and like it would just keep going on. So like these are all the issues that we find. Like so every single time
unless
like these
they're
issues
indexing, unless they're doing indexing at 1, not at 0, then this might make sense. But that's that's a whole new can of worms. I'm joking. Obviously, hopefully no one does that except for MATLAB.
Yeah. Oh yeah, MATLAB. I used to use MATLAB. Yeah. I did it for my math. Yeah, for MATLAB. But yes,
I remember myself. Yeah. I've used it myself back in the faculty. Cool. Do you
exactly.
I think we have 10ish more minutes. Do you maybe? I was thinking of potentially opening up a Triton kernel and walking us through how you think about optimizations such as when to do something in place or not to do it in place. And also, I know you had this matrix chain optimization where you basically decide on the order of how you want to do associativity of the matrices so as to optimize in the sense of minimizing flops. Can you maybe walk us through that example or the one I mentioned about in place in Triton? That would be, I think, useful if you have something at hand.
Yes. Yeah. So if you go to our GitHub repo, we do have all our kernels in our repo. Yes. So if you go to our kernels, right? So like, for example, the fast LoRa, I'm assuming you're talking about our fast LoRa implementation for our, so yeah, if you look in our GitHub repo, I can make it smaller a bit. Okay, I don't know if people can see, but like we actually derive these derivatives ourselves. You can actually see the derivatives, how we actually derive them, right? So like, for example, dc over dA, right, is equal to this gigantic formula. And essentially like, because you derive the formula, right? Now you can see, okay, you derive the formulas. Can we like bracket them correctly, right? So like depending on how you bracket, you can actually change, you can reduce flops and stuff like that, right? So like, should you bracket over here, right?
Got it.
Or should you bracket over here, right? And
so the thing here is you're dealing with 3 or 4 matrices. It's not like you have n matrices. You're not dealing with the general problem where you have to actually do some dynamic programming or whatnot to come up with an optimal solution. Here you can actually just try a couple of combinations and see what is that how you think about it, or you actually have something that's a bit more general?
Exactly. So if you do general optimization, there's like there's like libraries for you to like, do like automatic, like, checking which matrix should you bracket first, and you can do stuff like that. So there are like, I think PyTorch itself has like einsum. I don't remember. I think einsum, if you use PyTorch einsum, it actually automatically calculates the best. Like, someone actually told me about this. Like you can actually automatically, there we go, speed up computation to consume. You can optimize the actual contraction order. So like if you do A times B times C, D times E times, or F, right? It will firstly optimize to like see which one should you times first. And so like PyTorch kind of has this automatically now. And so you can actually just use this. But I think if you want to write the backprop, if you actually want to write the backprop in Triton, you can't use this automatic methodology, right? So like, you can't do like in place and stuff like that. So this is only for like, for general use case. Yeah.
So I would assume CUDA graphs probably later actually traces out the exact associativity of the chain, and you don't have that overhead of having to do that algorithm as opposed to just doing matmals, if you understand what I'm saying. So yeah,
I think sometimes it doesn't. So PyTorch, AutoGrad, and like the other ones probably won't be able to optimize this because like there's many steps in between. Like for example, this derivatives is probably a bit too complicated to derive. Like they have too many steps in the derivatives, so it's actually very hard to contract the graph. And so like you have to do this manually and contract the graph manually. And so like that's where the optimizations come from. Manual contraction of the graph.
And fusions and stuff. Yeah, compilers are dumb, as Horace always says, but like it's crazy they can even do as much as they can today.
Yeah. I highly, compilers like torture compile, like, using PyTorch, the PyTorch team is very, very good. And so like, they definitely know what they're doing. And so like, I'm assuming, so we had like a meeting with them as like, I'm assuming they're going to like learn how we do some stuff and then shove it into like PyTorch compiler. But yeah, generally compilers, like, yes, they're very dumb, but I think they're getting smarter and smarter and smarter.
How do you think about going from scratch as opposed to, I mean, as more people are building these kernels, obviously at one point the community will converge to more optimal solutions that are battle tested that you can just copy paste or whatnot, or maybe tweak a bit. How do you think about, did you ever use something like PyTorch to create the initial version of the Triton, which I know can be a bit obfuscated sometimes, and use that as inspiration as a starting point, or use an existing Triton kernel that maybe Phil has in his repository or Trida or somebody else was already has already built, which is not as obfuscated as the automatic one, and then use that as a starting point as opposed to starting from scratch? Do you kind of combine those three, or are you always like, hey, let's just go from scratch, and then you cross compare and see whether you're actually better than those other reference implementations?
Yeah, so like I generally fall back to the actual Triton documentation. They generally have like nice documentation for like, for tutorials, and like, they actually show some differentiation. They show like, for example, the attention Triton kernel. They show like the llm Triton kernel. So they do show some stuff for the Triton kernels. But yes, like I'm not just like sitting here like just writing Triton kernels. That probably take forever. So I do like look at like torture compiles output. I look at like what TreeDAO is doing, like flash attention. What are they doing? What are like other packages doing? It's like a cross pollination of ideas and stuff like that. And then finally we like sit down and like write our own Triton kernels and look and then finally we like optimize step by step and stuff like that. So it's not like we're just sitting here doing like a Triton kernels from scratch. It does require a whole collaboration. Yeah.
You're having epiphany moments, no pun intended, to my YouTube channel. Okay, so that's super cool. And so how would you describe what are maybe, when it comes to speedups, let's focus on the runtime. What would you say have been the three main bottlenecks that for example, are the reason why you're so faster than PyTorch or Hugging Face or any of those? As much as you can share. I know you have kind of tiers and that's completely fine. You're trying to build a business, but as much as you can share of how you see the bottlenecks for the runtime.
Yeah, for the open source. Yeah, specifically for the open source, like we find that if you do like Triton kernels, you can speed up some stuff. But that's not going to get you too far, right? So like even if you have Triton kernels and like trying to like make stuff faster by using lower level CUDA, you can only get so far. You have to use other methodologies in the open source, like reducing actual number of flops, right? Like reducing like contraction of the actual graph by reducing actual flops. That can get you much more reducing data movement. Don't do too many copies. Like doing stuff in place. All of these things, when you add them all together, you get the 2 times faster in the open source. But I think the biggest problem is like, for GPUs, you just have to be very careful. They really dislike data movement. So don't do too much data movement. And if you can do that, if you can solve the data movement component, you can generally get 2 times faster. And yeah, that's kind of like where the open source comes from, is like open source is just optimizing based on like reducing data movement, trying to do operations in place, reducing the, graph by contraction by like doing the manual order grad and stuff like that. Yeah.
Do you feel there is more performance to be squeezed out if you went to CUDA as opposed to Triton? And I don't know whether you're doing that in the background behind the scenes, but like, do you see like a big difference in terms of Triton versus CUDA right now?
No, I don't think so. So even if you use CUDA, you'll probably get like a 10% to 20% boost. It's not that much. So even if you change all of the Triton and just use CUDA, you'll probably get like 2.3 times. It's not that dramatic. 2.2 times. And I think the effort isn't really worth it because like you have to manually write, individual CUDA components for each one, and it'll be a nightmare to do. So I think like we generally just use Triton. We think Triton, like over time, Triton will get more optimized. We normally have the view that the compiler will get smarter. And so like we should augment our, package with compilers. And so like compilers are generally much smarter than us in general, right? Many people have like shoved all the optimizations in the compiler. And so like we'll rely on the compiler to do the last mile of optimization. We would just do the 2 times faster. If you want to get to 2.2 times faster, then yes, you should use like a, do automatic, do all the CUDA programming. But I think the effort is not worth it. Yeah.
Yeah. I think, am I wrong to say, I saw somewhere in your blog that you have even 30x, but that's for your pro tier or something. Was that an actual number I saw, or let me pick it up somewhere?
No, that's correct. That's correct. We do have a pro offering, which is 30 times faster. And our open source is around 2 times faster. And I think, so memory reduction, our open source is 70% memory reduction. Our pro version is like 90% memory reduction. And the trick we do is like, we always focus on no accuracy degradation. How do we like, reduce the degradation to try to go to 0 as much as possible? And we, don't do approximations for attention. Like, for example, don't use like state space models for like the attention component, use exact attention. And if you want to use exact attention, how do we actually optimize this correctly? And so like, that's kind of what we focus on, is like, try to like make, the accuracy degradation go to 0. But yes, it is 30 times correct. this is just an average. So like in general for data sets, we found it to be 30 times faster. For some data sets, it can be 60 times faster. Some data sets can be like, 15 to 20 times faster, but it depends on the data set. But in general, on average, it's 30 times faster. Yeah.
Got it. And you're using what as a reference there? Hugging Face, or what's the reference as you're comparing against?
Or reference. So whenever we say speed up, it's Hugging Face plus Splash Attention 2 plus 4-bit QLoRa. So we use the base implementation plus optimizations that people normally do. So that's generally what we use. Yeah.
Nice. It would be cool. I don't know if you've seen the llm.c project that got brought.
Yes, Andre. Yeah. No, they're fantastic. Yeah.
It's amazing. I have been contributing over the last week myself, found some nice bugs as well. So it was very, very nice for me to just invite you today and talk more about bug hunting. But I'm curious if you compared maybe against llm.c and see how, like, if you can compare at all, because llm.c currently just supports GPT-2. So there is no rope, there are none of those. But I don't think rope or any of those really change the runtime significantly at all.
No, so definitely llm.c for Andre Karpathy's package with the other contributors are very good. They generally compare to like Torch to compile, right? So like if you use Torch to compile and you compare llm.c for pre-training, generally they're generally equalized. I think llm.c is like 10 to 20% faster than Torch to compile. But I'm going to assume the PyTorch team, we know, like, they're very, very, very good at making stuff faster. So they probably already made it like, the same speed as llm.c, most likely probably by today. I know the engineers are very, very, very good. So they're very fantastic. But I think we can't exactly compare to llm.c. It's because we do fine tuning. And we do 4-bit QLoRa. And we have like other stuff in the package. So it's actually very hard to compare. If you want to compare direct pre-training, then I would just advise people to use Torch to compile and just use pre-training via Torch to compile. That's generally what I advise people to do.
You're mostly focusing on fine-tuning and in particular parameter-efficient types of fine-tunes, right? Or in general fine-tunes?
So we can do general fine-tuning as well. And I think the last time we checked, yes, we're still faster than Torch to compile. But obviously you can't do too much. Obviously they will learn our methodologies for Torch to compile for like pre-training and stuff like that. You can only do so far with pre-training because pre-training is very, it's very, very, very like it's like a set recipe for everyone, right? So like if you do Torch to compile, if you use like float 8, maybe you can make it faster a bit. But the problem now you have is like data movement and like data bandwidth. So you can only go so far with pre-training. But with fine-tuning specifically, you can do so many optimizations. You can do like QLoRa, 4-bit. There's so many stuff that you can do. And so it's very hard to actually compare directly as performance. Yeah.
Perfect. Thanks for clarifying. There was one question in the chat. Sorry, guys, we kind of were very like digging into details. It was hard to stop for a second and see whether people have questions. Maybe Daniel, if you have a couple more minutes, we can take a couple of questions from folks here. One is from Casey. Yep. Why should you do fine tuning over RAG? You want to take that one? I'm sure you have a couple.
No, I think like generally speaking, like RAG is very good if you have like a large data set and you want to just ask questions about it. Like, if you want to say like, pretend you have like all of Wikipedia and you shove it into the model. Now the model have like, the model has like some sort of like library of all the Wikipedia articles. And you can essentially ask questions about the model using the Wikipedia data set. But I think fine tuning is different because fine tuning, you actually allow you to like learn new skills. You can change the behavior of the model and you can actually like, increase the accuracy of some, components of the model. So like if you want to do RAG, it's okay, but this is only if you have a large data set that you already have available, and you just want to do like, question answer for the RAG system. But if you fine tuning is only useful if you want to actually change the model's behavior, if you want to learn new skills, and you want to like inject knowledge into the model, and that's where fine tuning comes in. Yeah.
Yeah, I would just add there, it's not one or the other. It just depends on your context. If you have enough data to do the fine tunes, it's almost a no-brainer. As long as you're careful not to have some catastrophic forgetting and lose capabilities that you don't want to lose. Yeah, go ahead. Daniel,
normally we would just suggest people to like do fine tuning, RAG, and prompting. Like you should use all three in one go. Generally, you should start with prompting, then RAG, then fine tuning. But in general, like because we make exercise so much faster and much easier to use, fine tuning and RAG is like on a similar footing now. Hopefully, yeah.
Awesome. There is one question from JP. When is the multi-GPU support coming for the open tier for Unsloth? Do you yeah, do you focus on multi-GPU even in your other tiers, or you're currently focused on just like single GPUs everywhere?
So the goal of Unsloth for now is like we want to increase accessibility for people, and like we want to. So we're adding like more model support. We're doing like compilation for every single model. So like once a new model comes out, it will automatically be supported. We generally wanted to be the best single GPU fine-tuning library. If the problem is when you support multi-GPU, the code can be very, very, very hard to maintain, and it becomes a nightmare to maintain. And so like our primary objective is to make a single GPU fine-tuning library the best. The majority of all users only have one GPU. That's kind of where the free, open source version comes in. It's like we want to optimize and make it the best. But for multi-GPU, yes, for our pro versions and for like our other versions, we do have multi-GPU. It is still under production, so it still requires some extra work to get there. But in general, our core focus is we want to be the best single GPU fine-tuning library for the entire world. That is our core focus. Yeah.
Perfect. That's super cool. And I guess going into multi GPU opens up a new can of worms when it comes to optimization and how do you overlap communication with computation and all of that. It just becomes much more complex. Let me see whether there was any more question. Can you discuss what's the? By the way, guys, feel free to raise your hand and ask a question if it's easier than typing it in. Can you discuss what is the future of reproducibility in ML research? Is there some sort of unit testing that's possible for these various implementations against a reference? I guess coming back to the whole thing and how you approach finding bugs and comparing against a reference, can we automate that? How can we make it easier for the community as a whole?
I think generally you could automate some component. I think it's actually very hard to automate the entire process. I think the problem is because language models and all these like new model architectures, they're still very new. And over time, I'm going to assume you can do like unit testing for each component. You can have like, specific automatic bug checking, like, we'll like contribute like some sort of like automatic bug checking fixes and stuff like that. I think we will going to work with the Hugging Face team on some sort of like automatic, bug fixes and like automatic checkers for models. But I think in general, I think the problem is like twofold. The first one is like, these model architectures, we want to like match the reference implementation as much as possible. So like generally that's the first thing that you have to focus. So it's like, how do we match the reference implementation? And the problem is like, there's so many other implementations. We don't know which one is the correct one. And so like, all of these implementations have to be edited to match the reference implementation. And that's actually it requires the work of the engineer behind the alternative implementations to like edit it to match the actual reference implementation. So it's like, it depends. And for the second problem is like, I think there's too many combinatorial problems. Like, is this one problem you can change? Is this one downcasting problem you can change? Is this another one you can change? And so essentially it requires a lot of, trial and error. And it's just very hard to automate. It's because like, I don't know how to say it. It's just very complicated to automate. I think we're working something internally which can automate some components. But it will still take a bit more time to like, it's not ready. So like once we release something like that, maybe that'll be helpful to the community. Yeah.
Perfect. Thanks, Daniel. I think we should wrap it up. Maybe Data has one more question. We can take that one and then we can wrap it up, being cognizant of your time and mine as well and others. Okay, Data, go ahead.
Yeah. So in the 2x increment that you quote, how much of it is just because of the matrix operation rearrangement and how much of it is because of Triton, and what contributes to how much percentage of the 2x increment? Can you shed some light on that?
Oh, we had a blog. Yeah, so for the optimizations, like we had a blog post on the Unsloth website which shows like which component contributes to which. So like does the matrix like how much percentage is a manual autograd, like the graph contraction, how much is that contributing to the time reduction? So there is a blog post we did on our Unsloth website. Yeah, it should be there somewhere. I think it's the second blog that we did, I think, or maybe the first one. And so if you look in our blog posts, there should be there on our, there should be a table for the stuff that you want. Yeah.
Cool. And is it consistent across models and architectures? Like Llama has for example, Gemma has wider architecture as compared to other Llama and Mistral. Like, so.
Sorry, what do you mean? Like you mean different architectures or?
Like in the sense, for example, Llama has like 4096 as the hidden dimension, and somewhere like Gemma has a wider architecture, right? Wider layers and a shallow network compared to Llama for 7B. So is the difference is the let's say we are getting 10% improvement by just rearranging matrix multiplications. Is the 10% similar between like Llama and Gemma, or is it like?
Oh, you're saying like because of different model architectures,
Yeah,
is the
exactly.
improvements like the percentage like similar? I would say it's generally similar. Like, you know, the percentages, they're going to change, obviously. Like, for example, Gemma is actually 2.4 times faster for the open source, right? So it's actually even faster than the 2 times that we generally show for Llama and Mistral. It's because of these like different architecture differences that makes it faster. I would just assume generally just like multiply. You know, I wouldn't say too much like, you know, which part contributes more and which part contributes less. I think it require like some manual inspection, but I think in general, the percentages hold up. So if like, you know, the manual autograd is like X times faster, makes it X times faster, it would just be like, you know, X times faster times 2.4 divided by 4. So it's just a bit more faster. So generally speaking, it's equal, like it's similar across the entire model architecture. Yeah, so it's like similar. Yeah.
Yeah, good. Makes sense.
Awesome. Daniel, thanks a ton for coming today and sharing with us your knowledge. This was really interesting for me personally, and I hope others enjoyed it. Judging by the comment section, I think people really liked it. I'll post a video likely already tomorrow or day after tomorrow, so people can watch it on YouTube if you missed the talk or join a bit later. So again, thanks for joining, Daniel.
Yeah, thanks for inviting and much appreciated, everyone. Thanks a lot. Yeah.